Analog measuring instruments. Northwest University, course ETEE 222. Learning Unit 3. Different types of multimeters. The older technology gave us analog multimeters. Current technology gives us the digital multimeter. And then we also have a specialist meter, which we call the insulation tester. Insulation tester, the purpose of which is to measure earth breakdown and contact faults. Select the 500 scale for 220 volts because the value must be at least twice the supply voltage. The high voltage breaks down the fault. You switch on the tester by pressing and turning the knob clockwise. Remember to switch it off again after use. Zeroing the analog multimeter, the purpose of which is to align the needle to the zero mark. To do that, you have to short out the leads and adjust the zeroing knob so that the needle rests exactly on the zero mark. Normal position of the zeroing knob. Identifying and using the different scales. For ohms, in other words resistance readings, select the ×1 scale for measuring the continuity for very low readings, increase scale for higher readings. Read the resistance in ohms on this calibrated dial. For reading volts, select AC or DC, both readings on volts calibrated dial. Get the appropriate volts reading on this calibrated dial. For current readings, select the DC only scale and it uses the volts calibrated dial. Normally, select the highest scale possible and go lower if the scale is too big. Taking the correct readings. Have a look at the following calibrated dials. The top display is meant for reading resistance. The next three displays is meant to read DC volts and amps. The bottom display uses the same numbers but is connected to the AC volts reading. The scale used indicates the maximum reading. For instance, if I take the ×500 scale, the maximum reading I can do is of course 500. But any reading for DC voltage must now get a 0 added. Therefore, the needle where it is at this moment will indicate 220 volt on the ×50 scale. Because maximum voltage on this scale and this setting will then be 500 volts. You can now apply this principle for any scale you use. Now let us take a reading on the ×10 scale for ohms. Determine the reading for the needle's position. Stop the video now. You have 3 seconds to do that. The reading is 260 ohms. Now apply this same principle to all the other exercises. Using the same needle position, get the DC volts reading for the ×50 scale. Stop the video. The correct reading is 22 volts on the ×50 scale. Get the AC voltage on the ×250 scale. Stop video. The correct reading is 110.5 volts on the 250 scale on the bottom display. For reading DC amps, the scale is divided into milliamps and microamps. If the scale indicates 250 milliamps, you have to read from the 250 scale. If it indicates 25 milliamps, then of course you must also read it on the 250 scale. But then the maximum reading can only be 25 milliamperes. In other words, dividing by 10. Now try the next reading for the needle position. Now try the next reading on the 100 milliamp scale. To stop, you've got 3 seconds. The correct answer is 44 milliamperes. For reading AC amps, rather use a tong tester. Sensitivity and input impedance. When this meter is used for measuring voltage, the input impedance of the multimeter must be very high compared to the impedance of the circuit being measured. Otherwise, circuit operation may be affected and the reading will be inaccurate because of parallel measurement. Sensitivity should not be confused with resolution of a meter, which is defined as the lowest signal change, in other words voltage, current, resistance and so on, that can change the observed reading. Expressing sensitivity. Most analog multimeters of the moving pointer type are unbuffered and draw current from the circuit under test to deflect the meter pointer. The impedance of the meter varies depending on the basic sensitivity of the meter movement and the range which is selected. For example, a meter with a typical 20,000 ohm per volt sensitivity will have an input resistance of 2 megohms at the 100 volt range, that is 100 volts times 20,000 ohm per volt, and that will give you 2 million ohms per volt. On every range at full scale voltage of the range, the full current required to deflect the meter movement is taken from the circuit under test. AC to DC conversion through a rectifier bridge. Since the basic indicator system in either an analog or digital meter responds to DC only, a multimeter includes an AC to DC conversion circuit for making alternating current measurements. Basic meters utilize a rectifier circuit to measure the average or peak absolute value of the voltage, but are calibrated to show the calculated root mean square, or otherwise also referred to as RMS, value for a sinusoidal waveform. This will give correct readings for alternating current as used in power distribution. Of course, RMS value of a sine wave form will give the same value of a corresponding DC value. Digital multimeters generally take measurements with accuracy superior to their analog counterparts. Standard analog multimeters measure with typically plus-minus 3% accuracy, though instruments of higher accuracy are made. Standard portable digital multimeters are specified to have an accuracy of typically plus-minus 0.5% on the DC voltage ranges. Mainstream benchtop multimeters are available with specified accuracy of better than plus-minus 0.01%. Laboratory grade instruments can have accuracies of a few parts per million. Moving coil and iron meter with dampening mechanisms. The moving coil, which drives the pointer needle, can be prevented from swaying by using a spring as indicated. The moving iron type is normally dampened with a diaphragm inside a chamber. It makes use of the resistance of the air against movement. Correct connections to circuits. Measuring current is always in series with the meter. As indicated, the two probes forms part of the circuit. Measuring voltages is always in parallel with the potential difference or EMF you want to measure. As you can see, the probes are in parallel with the load under test. Resistance is measured directly over the connections of the resistor, normally outside of any circuit, because other parts of the circuit can influence the resistance measurement. We need a shunt resistance to measure different currents. If the meter uses 100 milliamperes for a full-scale reading, it actually means that the meter cannot handle more than 100 milliamperes. Therefore, we have to supply a shunt resistor to bypass the meter, which is indicated by Rs. Another factor we must remember is that the meter itself has got an internal resistance called Rm. In this case, it is 5 ohms. The shunt resistor will bypass most of the current. Current through meter is 100 milliampere, that is for a full-scale reading. If we want to measure 10 amperes, we need to shunt most of the current through the shunt resistor. If we subtract 100 milliamperes from 10 amperes, we can determine the shunt current. In this case, 9,9 ampere. Now we can determine what is the potential difference over the internal resistance. So, potential difference Rm equals I FSR times Rm, and that will equal 100 milliamperes times 5, which is the internal resistor, and that will give us 0,5 volts. Now remember, the current through Rs must be able to handle 9,9 amperes. Now let us determine what is the potential difference over Rs. It is 0,5 volts. Why? Because parallel resistances like Rm and Rs will always have the same value. Now we can determine what the value of Rs will be. Using Ohm's law, R equals V over I, that is 0,5 over 9,9. The shunt resistor's value will then be 0,05 ohms or 50 milliohms. Any current can now be measured if Rs is adjusted to the correct value. Do the following exercise. Stop the video here and work out what the Rs or shunt resistor will be in this specific instance. Stop it now and check the answer on the next slide. The answer for Ishunt is 0,021 ohms. Measuring different voltages, we need a series resistor to take up most of the potential difference. Let us consider the next scenario. Im equals 100 milliamperes and Rm, that's the internal resistance, equals 3 ohms. Rs1 and Rs2 represents two different scale selections. As we have said, Im for FSR equals 100 milliamperes. Now we can determine what the maximum potential difference across Rm or R internal will be. Of course, according to Ohm's law, Im times Rm equals 100 times 10 to the power minus 3 times 3, which is R internal, will then give us a potential difference of 300 millivolts. Now let us calculate the series resistor. Subtracting 300 millivolts from 100 volts, the potential difference across Rs will have to take 99.7 volts if we want to measure 100 volts. That gives us Rs now equals potential difference of Rs over Im, which is 99.7 over 100 times 10 to the power minus 3. Therefore, the shunt resistor must be 997 ohms to be able to measure 100 volts maximum. Stop the video and do the next exercise. The answer will be displayed in the next slide. Stop now. The answer for R series is 997 ohm. This is now the end for study unit 3. Make sure that you understand everything, because we will write an online test in the not too distant future. Do some extracurricular reading so as to familiarize yourself with all aspects of measuring electrical parameters.